Okay, hi again. So, quick addendum to the first video, and that was that I talked about the gravitational force acting on a person because of the Earth's gravitational field. Right? I just want to mention, just quick, Newton's third law says that for every action there's an equal and opposite reaction, that forces come in action-reaction pairs. So even though the stuff that I've got up here doesn't apply to that because I've already rubbed it out to make way for the new stuff, just keep in mind that if there's a force of 586 newtons on the Earth exerted by the gravitational, on the person exerted by the Earth's gravitational field, there is a reaction force to that, a force of 586 newtons acting on the Earth due to the person's gravitational field. So you've got that action-reaction pair between the two gravitational forces. The forces are equal to each other, but the force of the Earth's gravitational field on the person is going to be more apparent because the person has a smaller mass. We know from Newton's second law that F equals ma, or A equals F divided by m, which means that if you've got the same force on two objects, but one has a much larger mass, then the acceleration on that larger mass is going to be much smaller. The effect of that force is going to be much less apparent. So you see a large effect on the person because of the Earth's gravitational field, because the person has a much smaller mass than the Earth. You see less of an impact on the Earth because of the person's gravitational field, because the Earth has such a large mass. But the forces between those two objects, the gravitational forces, are going to be identical to each other in terms of their strength, although opposite in direction. Just because force being a vector quantity, you've got to worry about the direction as well. But the point is, the magnitudes are equal. Just keep that in mind, that when I did that calculation, it was the force on the person by the Earth, also the force on the Earth by the person. So anyway, moving on to the second part of this topic. Hopefully I can get this working. This is going to be a bit of a learning thing. Also going to talk about something called apparent weight. And this is going to, it seems like it's just popping up out of nowhere, but it's going to really tie in with what we're doing in future lessons. So when we're talking about apparent weight, we're really talking about the normal force exerted on an object or on a person by, well, the ground, because this person in the example is in an elevator. The bottom of the elevator is pushing on them. There's a normal force on them as a result. So we did this earlier in the year. I said we'd go back to this, and it worked well when we were talking about circular motion. We used a certain approach with vectors that kind of ties in with this. So we're going back to this, and we're going to be focusing more on apparent weight and the concepts around that, in addition to, well, those kind of force calculations that we were doing earlier. So with one like this, you've got a person in an elevator, starts at the bottom, it accelerates upwards. So because it's accelerating upwards, there's going to be a net force acting upwards on this person. In the middle, halfway along their course, they've got an acceleration of 0. They're moving in the constant speed, so there's going to be 0 net force. And once they get to the top of their path, they're going to slow down as well, and slow down now, and have a downwards acceleration as a result. So since they have a downwards acceleration here, we're just going to write that F net is going to be down. So F net up, F net equals 0, and then F net equals, well, it's downwards. Now I said F net equals downwards, or F net equals, we can calculate what F net is going to be in each case. So in the first case over here, we've got that F net, we're focusing on the mass of the person and what's going on with them, so we don't have to worry about the mass of the elevator. In this case, we've just got F net equals ma, so equals the person's mass of 50 times their acceleration of 2. They've got a net force on them of 100 newtons as a result. Second one, F net is 0, ma, so mass times 0 gets us our 0 value. And because this is minus 2, we can just tell straight away that F net is going to be the same magnitude, but it's just going to be negative 100 newtons. So it's just going to be directed downwards as a result. So I know my net force is in these three situations, but going back to the start, what I'm after is the apparent weight. And that's going to be equal to the normal force on them. So what I want to find in each of these cases is the person's apparent weight at each point in time, what the normal force would be on them there, there, and there. I haven't written that up, but that's going to be the gist of what this question is about. So to get the normal force, I'm also going to need one other thing. The net force acting on them, and my black and blue markers seem like they come through really well on the screen. My red and green markers not so much, but you know, let's try. So we've got two forces acting on the person that combine together to get us the net force. Those two forces are the weight force pulling down, that's their weight force there, and the normal force pushing up on the person. Now, going back to our vector stuff, we've got a downwards vector, we've got an upwards vector. Those two combine together. Yeah, that's not coming through. I'm going to switch back to blue. When we combine our normal force and our weight force, we get a net force that's pointing up overall, which implies that the normal force has to be bigger than the weight force, so that when we combine this upwards one with this downwards one, we get an overall upwards force. So this one in this situation, the normal, has to be the larger force. It has to be bigger than the weight force. Go away, Apple ID verification. Okay, second scenario, we've got a weight force down, that's Fg. We've got a normal force up, Fn. Because we've got a net force of 0, those two forces have to exactly balance each other out, so I've drawn them to be the same size as each other. Third scenario, we've got a weight force down, we've got a normal force up. The overall force, the net force, is downwards, which implies that the weight force has to be stronger now than the normal force. So the weight force, that's your mass times gravity, that's going to be a constant value. The person's mass isn't changing and they're not going up so high that gravity is changing in value. So we're going to assume that the weight force is constant throughout the entire trip. The normal force, though, it's going to change in value because of the way that the acceleration of the person and the elevator is changing throughout the course. So here we've got a large normal force. The elevator is pushing someone up and causing them to accelerate upwards. Here we've got a small normal force because there's less acceleration, less force needed to push them up. And here we've got the smallest normal force because that's when their acceleration is downwards, so the floor is going to be pushing on them less than it had been throughout the other parts of the trip. So anyway, that's the conceptual stuff. Now we'll do the calculation stuff. So here's another whiteboard. Hopefully it's not going to vanish into nowhere. Yeah, that works. Just try and recenter it. Okay, so I'm going to try and calculate the normal force at each point in the trip. So for the point over here, we've got our net force, and that's pointing in the upwards direction. So I've defined upwards as being positive. Can you see what I'm writing on the screen? I hope so. Because I've defined upwards as positive, I'm going to say that Fn, which is also upwards, is also going to be positive. Fg, which is pointing downwards, is going to be a negative value. So I put a negative sign in front of that. So I know most of the numbers for this already. I know that Fnet is going to be 100 newtons. I don't know Fn, my normal force, that's what I find. Fg, that's just going to be mass times gravity. It's going to be 50 times 9.8. So then I can do a rearrangement of this, and I'm going to get out that Fn is going to just be 100 plus, that's 490. So the normal force is just going to be 590 newtons. Cool. So that's my normal force at this point in time. 590 newtons. It's stronger than the weight force, which was 490. That jives with what I expect. I expect my normal force to be bigger than my weight force, so that when I combine those two together, I do get a net force that's pointing upwards in the same direction as the normal force. Second case, this one, can you still see? Sorry if I'm being super paranoid about this, I just don't want the videos to be crap. So for this one, we've got F net equals 0. So it doesn't really matter if we define that as positive or negative. We've got equals the normal force minus the weight force. So again, I've just said upwards is positive. I'm going to stick with that convention throughout my whole thing, although if I didn't, then I'd still get the same answers. F net is 0. F normal is what I want to find, and this again is just 490. Rearranging, that's pretty straightforward. The normal force is just going to be 490 newtons. So now my normal force is less than it was over here. It's decreased because the acceleration is no longer upwards. It's now equal to the weight force, which is what I expect conceptually, because these two forces should balance each other out in order to get me a net force of 0, since there's no acceleration at that point. So this is going to be my third situation. Now I've got my net force. I'll again define upwards as positive because I've said that this is downwards and negative, so I'm going to stick with my convention. F net equals F normal minus Fg. Negative 100 equals F net minus 490. You do that calculation and you get out that the normal force is now going to be 300 and that checks out, doesn't it? 390 newtons. And yeah, you can see that, I hope. Okay, so normal force smaller than it was at either of the previous 2 points. So that jives with what I expect. This is less than that, so that when I combine the normal force and the weight force, I get a downwards vector. So this is conceptually, it seems like it's going to be right. So I found the normal force at each point along here. I can say that this is the apparent weight at this point, 509 newtons. The apparent weight is 490. The apparent weight here is 390. So at the beginning, the person's going to feel that they weigh more, they have more apparent weight than they normally would. And that kind of works with what you'd know if you've been in an elevator. You know that when it starts going up, the elevator's pushing on you and making you feel like you're a bit heavier. Normally when I'm in an elevator and it's going up, I like to bend my knees to kind of reinforce myself. Just make sure that, you know, I'm not feeling uncomfortable. The reason that happens is just because there is a larger apparent weight. You feel heavier and you've got to kind of, you know, buckle yourself in so that you're not getting pushed around unpleasantly. When you get to the top of the elevator and it starts slowing down, I like to just stand on my tippy toes because, well, there's less weight on me. I feel lighter as a result. I don't know why I stand on my tiptoes, really. It just feels cool. But the point is that at the beginning, when your acceleration is upwards, you've got a larger normal force on you, so more apparent weight. In the middle, your apparent weight is equal to the weight force on you, so it's like being in a normal situation, just standing around. And towards the top, when the acceleration's downwards, you've got a smaller apparent weight than you normally would. You feel lighter as a result. So I could do more on these examples, but just want to keep videos reasonably short. This one's already 12 minutes. So that's all the stuff to do with apparent weight. Now, these 2 videos, the one I recorded before and the one I'm recording now, they are from the stuff on chapter 1.1. I've uploaded to Compass a lesson plan that says lesson 1, you need to be going to this chapter, doing these questions from Heinemann, and then doing the checkpoints questions from whichever chapter I've set that from. So work solutions for these questions are available on Compass under Physics and then under Resources. They're under Heinemann Solutions. That's the folder you'll find them under. So chapter 1 solutions, you can get through to there. So if you're unsure about how to answer any of the questions, you can always consult those. If you're not sure still after that, just send me through an email. I've got your email addresses, so I'll just reply to that email if I get an email from you. Please use the checkpoints questions and do those. I know that it's easy to just do the Heinemann questions and feel you've got a good handle on all the concepts, but you want to make sure you're using this opportunity to get those checkpoints questions done. There are work solutions for those as well on Compass. They're updated now to the 2020 version of checkpoints. If you don't have a checkpoints book, I have a copy. It might be worth you coming in to school at some point, grabbing one off me. I guess first in, best dressed, but I really do want you to be getting those questions done because they're going to extend your understanding of what you need to know, and they're going to provide more challenging versions of the basic concepts that you learn when you do those Heinemann questions from your textbook. Also, you've got Ed Rollo. I know I'm filming these videos and maybe they're enough, maybe they're not, I don't know. But please get onto Ed Rollo and try watching videos from there because they'll provide a different point of view on the topics that we're going to be looking at. So this was the first lesson, 1.1, stuff on gravitational forces. I'm going to record the next video right now. I don't know, but we will see.